This is section 2.1. We're talking about using inductive reasoning. And we already talked about this in class, but let's look at example 1 if we're describing a visual pattern, and we'll move on to numerical patterns later. It says, describe how to sketch the fourth figure in the pattern, then sketch the fourth figure. So if we're looking at the pattern we have here, we have figures 1, 2, and 3, and there's certain things we can look at that are changing from figure 1 to figure 2 to figure 3. First of all, figure 1, we only have one dividing line. Figure 2, we have 2 dividing lines. In figure 3, we have 3 dividing lines. So we can assume that in figure 4, we'll have 4 dividing lines. So that's the first thing. The second thing is in figure 1, we are divided into halves. Figure 2, we're divided into fourths. Figure 3, we're divided into sixths. And thirdly, as fractions, I can write those. And I notice my denominator is increasing by 1. So if I went from 1/2 to 1/4 to 1/6, I can assume this would be 1/8. And again, I'll have 4 dividing lines, so I'll divide it into fourths, and then cut my fourths in half. So I have 4 lines. Now I've divided into eighths, and I shade one portion just like all the others have been shaded. So I kind of described it as I was going, and that's the actual sketch of the fourth figure. You're just looking at the pattern, what you have, and predicting what will come next. So that's how you do it with a visual pattern. Let's look at something with numerical value. So describing a number pattern. Directions say describe the pattern in the numbers -7, -21, -63, -189. And the 3 dots assume that the pattern is going to continue. And write the next 3 numbers in the pattern. So if we were to describe how are our numbers changing, how do we go from -7 to -21, and -21 to -63, and so on? Did we add something? Did we subtract? Did we multiply? Did we divide? Well, in this case, our numbers themselves, although they're negative, the numbers themselves are growing. Technically, since they're negatives, they're shrinking, but we're looking just at the numbers, they are growing. So we're either adding or multiplying. It looks like here we're not adding the same thing because here I add 14, or really subtract 14, I should say. So let's look at it that way because we're dealing with negatives. So if I subtract 14, I end up with -21. But then if I subtract 14 again, I do not end with -63. So since I'm not subtracting by the same number every time, it's probably not subtraction. So let's test multiplication since our numbers are growing. -7 times 3 is -21. -21 times 3 is -63. -63 times 3 is -189. So it looks like that if we were to describe our pattern, it's that we're multiplying. I'm just going to put mult as abbreviation. Multiplying by 3. So then we'll find our next 3 numbers in the pattern. So if I were to multiply my 189 by 3, I would end up with -567 as the next number in our pattern. If I multiply -567 by 3, I have a result of -1,701. And if I multiply that times 3, I end up with -5,103. And those are the next 3 terms in our pattern. So again, you always need to, when you're dealing with a number pattern like this, you need to identify what is changing. Are we multiplying, subtracting? Are we dividing? Are we adding? What is going on? And then when you identify that, you can predict your next 3 terms. And this is what we did in class. We exchanged problems, so let's move on from that. Example 3, making what's called a conjecture. So let's read the directions, and then we'll go over a couple definitions. Given 5 collinear points, collinear again meaning they are on the same line, make a conjecture, what's that? About the number of ways to connect different pairs of the points, so connecting any 2 points. Well, a conjecture is a math term that means it is an unproven statement based upon observations. Somewhat like a hypothesis is called in chemistry or biology, where you make an educated guess about something and then you do a test, an experiment, and you test whether it was true or false. So that's a conjecture. In math, we call it a conjecture. We do not call it a hypothesis because a hypothesis is something else in geometry, which we will see in the next section. Now, inductive reasoning, what we're talking about today, is full of conjectures. Inductive reasoning is finding a pattern like we did in the past 2 examples, and writing a conjecture or a rule like we did a description of what is happening, what the pattern is. That's inductive reasoning. We did that with the pictures, we did that with the numbers. So for this problem, given 5 collinear points, we're going to make a conjecture or an educated guess, a hypothesis, which we'll get away from calling it that, about the number of ways to connect different pairs of the points. So let's start by looking at the first 4 cases, identify the pattern, and then look at the 5th case. So let's start with 1 point. If we have one single point, let me change the color there, how many different ways can we connect those? Well, we don't really have multiple points, so there's really 0 number of ways we can connect them, so that doesn't really matter. If we had 2 points, there's really only one way we can connect those 2 points, and that's just one to the other. So we have one connection possible. If we have 3 points, and at any time you would like, you can pause this and then check your work with me if you want to do this on your own. We can connect the first one to the second one, the first to the third, or the second to the third. So for this particular step, with 3 collinear points, we have 3 possible connections. Okay, let's look at the 4th one and see if we can identify our pattern, because we might have an idea so far, but let's just be sure. For 4 collinear points, I can connect the first to the second, first to the third, or first to the fourth. I can also connect the second to the third and the second to the fourth. And finally, I can also connect my third to my fourth. So I have 1, 2, 3, 4, 5, 6 connections here. 6 ways I can connect to those points. So the first thing we need to do is make a conjecture. Let's identify the pattern here. Well, going from 0 connections to 1 connection, we added 1. Going from 1 connection to 3 connections, we added 2. And going from 3 connections to 6, we added 3. So you're probably seeing the pattern. The next one will probably add 4 and end up with 10. And we'll test that to see if it's true. So that's our conjecture. If we were to write a more of a rule for this, though, we would say something like the number of connections. I'm going to put in the hashtag for numbers. So the number of connections increases by 1 more each time. Or not really 1 more each time, but by 1 more than the last step. And there's probably a better way to phrase that, but for now we'll just leave it as that, since we're kind of just doing this, we're trying to write something out we discussed in class. So we added 1, then 2, then 3, then 4, and then we should probably add 5, then 6, etc. So let's draw our 5 collinear points and test to see if this conjecture is true. Which you're probably pretty confident it is, otherwise we probably wouldn't be going over this long of a problem. So, but again, I could have a trick up my sleeve and be looking for a specific point. Anyway, so I can connect point 1 to 2, 1 to 3, 1 to 4, and 1 to 5. And then we do different colors so this doesn't get too confusing. I can connect point 2 to 3, 2 to 4, 2 to 5. I can connect point 3 to point 5, point 3 to point 4. And lastly, I can connect the last 2. So if I were to count these, I have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Correct. Those are all my connections. Our conjecture was true. All right, for this example, we're looking at making and testing a conjecture. So we're looking at some numbers. The directions say numbers such as 3, 4, and 5 are called consecutive integers, meaning they appear one right after the other, and they're integers, so they're positive or negative whole numbers. Make and test a conjecture about the sum of any 3 consecutive integers. Well, let's make a few different examples, and then we'll see what pattern we notice with the sum of these consecutive integers. So an example, instead of 3, 4, and 5, let's choose 6, 7, and 8. And if we add 6, 7, and 8 together, our result is 21. So there's one example of 3 consecutive integers. Let's take another example. Let's do 10, 11, and 12. If we add 10, 11, and 12 together, I want to say we end up with 33. And that's our result. And for one more in our pattern, let's say we're going to take, let's do 1, 2, and 3. It's some really small numbers. And that gives us a result of 6. It says, come up with a conjecture here for the sums. So we're looking at these sums. So what do we notice these three sums have in common? Well, a good conjecture probably is that all three of those are divisible by 3. 21 is divisible by 3. Your result is 7. 33 divided by 3 is 11. And 6 divided by 3 is 2. So for our conjecture, we can say all are divisible by 3. So that's how we make and test a conjecture with something with consecutive integers. Let's look at one more definition and we'll be finished with the video. Find a counterexample to disprove each conjecture. Well, a counterexample is related to the actual word. It's an example that proves a conjecture to be false or disproves a conjecture. So for example, with some real life instances, let's say all soft drinks are made by Pepsi. Well, that's false, and a counterexample that disproves that is Coca-Cola. It's a counterexample that shows that statement that all soft drinks are made by Pepsi, that statement is false. If we look at example 2, the only food service that delivers pizza is Domino's. I think everybody in my classes today talked about Beggar's Pizza also being a food service that delivers pizza. So Beggar's would be a counterexample. Even though I said earlier I don't like beggars and there was uproar in 2 of my classes. You can hear uproar in the background even now. Number 3, all NBA teams are from the Midwest. All my classes today gave me the same counterexample of a team that is not from the Midwest, and that is the Miami Heat. Whether or not you like the Heat or not, that is our counterexample. So those are all examples of counterexamples. They simply prove your statement to be false. That concludes section 2.1. Feel free to pause and rewind and look at anything else that you need to.